and it was basic theorem for projective geometry, which developed further in the future. So I shall dissert a bit about that. And in projective geometry, there is a famous theorem about both perspectives. Let's say about trisectors first, which is the Molar Theorem, which is a special equilateral triangle, a bit magic, in the family of the triangles which are generated by the intersection of trisectors. And okay. So I shall try to put things, if I can have a joke, in perspective. So show that the Molar Theorem is something between many things. So first, I come with the definition of a linear perspective. Yes. So you see that you have two triangles here. One is the one I call the reference triangle, which is an integer triangle, 12, 13, 14, and which I have chosen because it has really no special property other than being an integer triangle. And inside, I have drawn the triangle of the altitudes with the orthocenter, and it is a well-known property that the altitudes cross at the same point. So the point, in that case, the common point, is the center of perspective of the reference triangle and of the altitudes triangle here. So that is the basic definition of a perspective. And what Desargues adds to that is that when you take the intersections of the sides of each triangle which are in perspective, they cross at 3 points, and these 3 points lie on the same line, which is the Desargues line. And that was really the discovery. By the way, it's very simple to prove, especially when you see the perspective as a kind of projection of two triangles with the same pyramid, but and the Desargues line is the intersection of the planes of the two triangles, but I shall not insist on that. Now we shall review a bit the properties of the perspective. First, is it reflexive? So, if, in other terms, is a triangle in perspective with itself? The answer is yes. And as a matter of fact, it is rather undefined because any point in the plane can be the center of perspective. And second point, the Desargues line is the infinity line because each side intersects with itself. So the common intersections is at infinity. Second question, is the perspective symmetric? So if T1 is in perspective with T2, is T2 in perspective with T1? The answer is yes. No, it's pretty obvious. Another point is the transitivity. If you have three triangles and T1 is in perspective with T2, T2 with T3, is T1 in perspective with T3? That is, in general, wrong. If you take, for instance, instead of the triangle of the altitudes, the triangle of the bisectors, both altitudes and bisectors are in perspective with the initial triangle 2T, but they are not in perspective between them. So, in general, the perspective is not transitive. nevertheless, it may happen that it is. So there are never, let's say, clear-cut rules to say that if I have these properties, it will not true. It may be true in some special cases. And I give an example here of homothetic triangles. And in that case, the property of transitivity is verified. Now, something important is the uniqueness. Is the perspective uniquely defined for two triangles which are in perspective? This is, the answer is yes, but there may be more than one center for the perspective. So this is a bit strange, but we shall see examples. And you can have up to 3 centers for the same perspective. Okay, and at the bottom. Yes, you have automatic perspective, for instance, when 2 triangles share the same side. That is, if you think a little, it's easy. It's the same for 2 triangles having the same vertex. But when the triangles have nothing in common, it becomes not obvious. Last, I said that there were elements at infinity. So let's say in the study of perspective, the business of parallel lines is a nightmare if you do not define points which, let's say, intersecting points which are always there. So the trick is to define special 3-coordinate point, which is the projective point, which has a 3rd coordinate, which in general is non-zero. But if it is 0, the point is at infinity in some direction. And also you can, as I said for the uniqueness, you can have lines at infinity. So now we come to the application. So I shall enlarge this figure. So you have the reference triangle, and all the trisectors are drawn here. And I added in gray the Molar triangle. But that was just to fix ideas. And what we shall do, instead of choosing special intersections like that, I shall take all possible ways, well, let's say all is a bit ambitious, but many possible ways of connecting the intersections. So the Molar triangle is one way of connecting 3, 6, and 11, but you can see that there are many other ways. And the number of triangles, by the way, may be gigantic. That is the reason why I said in the title that this question was an entry to complexity. So instead of studying one thing at a time, we study families of objects at a time. So in order to get some order, let's say, in all these possibilities, I classified them into 3 groups. Triangles, and the first group is the triangles which have a side in common with the reference triangle. So you can see all the combinations of this special construction here in the, and I treat only those which are in common with BC, because I guess that the other combinations with AC and AB in common is just a replica. This is the result of the Desargues function, which tests the perspective between each triangle and the reference triangle. And the net result is that all the centers are aligned on BC, on the side BC, and the Desargues line is also collinear to BC. So it is a very special case, nevertheless, it's simple, and we shall see that complexity comes a little later. So I have, in the previous figure, I have considered perspective with the reference triangle. Here, I consider perspective within the family of the triangles which share BC. And this is drawn here, and you can see that figure become richer. Still, the centers of perspective are still on BC, but when you look close, you see that here you have two lines of sight which converge at the same point. Same thing here. So you see in that jungle of combinations, you have special things which are a bit like, and if you detail them, yes, here, I have studied them especially. I extracted the perspectives here, and the way it can be read is the following. You have the reference triangle here, and in the other triangles, you have two perspectives. One between this one and this one, which is centered, by the way, on a Morley vertex. And it has this line of sight with this center of perspective, and a second perspective, which is between this one and this one. And the line of sight converges also here. And if you go to the other side here, you have exactly the same construction. So you find in that, what I call the jungle of perspective, two couples which have special properties. Now, we, after studying the families which have a side in common with T, we study the families which have a vertex in common. So you can see that the complexity here increases because each family with each angle has 198 triangles. And what will be interesting in that? So here, to have a global view of all these families, I define a new concept, which is the perspective space, in which I regroup all the centers, all the Desargues lines in a same graph. And doing that, you observe that all the centers and Desargues lines that you have defined, many of them are common. So which creates already a simplification in the landscape of the perspectives. And here, you have the 20, in the above figure, you have the 20 centers common to TA, TB, and TC. And you see they are distributed on the intersections, but not all of them. You have two in the center, let's say near the center of Molar Theorem, of Morley triangle, and others which are outside. And what is amusing also is that they are distributed not on, but around the bisectors, not the tri, but the bisectors. And here I have added all the other centers which are not common. So you have a kind of sky with stars, and we shall come back to the cluster, which is here a little later. Now, I have talked about the perspective space for centers of perspective, but you can put also in that space the Desargues lines. And it is what is done in the figure here. You see, at each vertex of the triangle, you have a pencil of lines, which for vertex A are drawn in red, for the vertex B in green and for the vertex C in blue. So I can do the same investigation that I did previously, looking if in that figure there are some special points. And I can see that these Desargues lines cross to form triangles. And you have families of triangles and pencils. And the question is, does some lines from the pencil cross at a vertex of a triangle? And the answer is yes. I shall show you just in a moment. To do that, I consider 6 special intersections. I shall not insist on that, but which have the peculiarity of not having common trisectors. And these special triangles, say, go to the, when you examine their perspective space, you can prove that they have the property that you see in A, you have a red Desargues line and a blue one, each corresponding to, to show you that. Yes, you have two triangles common to A. You see the blue one, which is stretched, not easy to see, and the red one, and it is the same for B and C. So the stretched triangles have Desargues lines which are blue, and regular triangles have Desargues lines which are red. And when you combine them, you see that they form a kind of magic triangle, a Desargues triangle in red, which by the common intersections of the blue lines, it becomes in perspective, this is a discovery, with the triangle ABC. See? And so that is a kind of new theorem. It was not known, I think, in the past. Now, time goes, but I come to the last part. I consider the triangles now which have no common element with the reference triangle. And they are drawn here in the figure. And there are 202. So in that case, you see, the perspective with the reference triangle is not automatic, as it was for the 2 previous families. So when I launch the function which describes the perspective called Desargues, it says that sometimes, and as a matter of fact, rather often, the triangles are not in perspective, which is normal, but some are. And those which are in perspective are drawn in that table here. You see, there are 100 perspectives. And you say, okay, but what is interesting there? So when you look, you see that many of them are, I would say, more or less obvious. They have the centers of perspective on the vertex of a triangle. And the Desargues line is either on one side or the other. Okay, so that is, and in these, I would say, more or less straightforward perspectives, there is one set which is rather amusing because it has 3 centers of perspectives. And it is drawn here. And it's kind of game. You can take this figure and look at the 3 perspectives, or let's say, how the 3 centers of the same perspective act to put various sides in on the lines of sight. And the Desargues line is always BC in that case. So that's a subset, if you like, of a bit intriguing perspectives with three centers. Now, in the same way, I discussed peculiarities in the previous section. I redo the perspective for the subset of intersections which do not involve common trisectors. And in that case, I reduce the number of combinations to drastically to 8, I think. Yes, to 8. And this is the result. So you can find the same perspectives in the above table, but here they are isolated. And the point is, when you consider that, you have no longer the centers of perspective at the vertices. They are elsewhere. So we shall study the perspective space of that subset. And let's say I shall enlarge it because it is really rich. So I'm tempted to describe that figure as a kind of sky where the centers of perspectives are small stars. And they happen, these centers of perspectives of the subset, to be aligned on some magic lines, either the blue lines or the red lines. And at the center of the, let's say, near the center of the triangle, you have what I call a double star, because it is each element of the double star is the vertex of a pencil, either blue or red. So you can see that there is an organization of that centers of perspective. And moreover, is that when you draw the triangles which are associated with 3 and 7, you find two triangles, the red one and the blue one. And you say that triangles who belong to the original, which belong to the original family, they must have some special property. So you test them if they are equilateral or not, for instance. So the test is here, and the red triangle is as the number 3, the blue one as the number 7, and you find that indeed the 3 is equilateral, but the second one is not. So in that organization of the perspective space, you find the famous Molar triangle here, but you see it is embedded in a perspective space which has also its own richness. It is not the only peculiarity. The others are aligned in a well-defined way. So now this is okay, almost time. This is the last figure. If in the same perspective space I draw the Desargues line, I find that figure, and I generate a new family of triangles which has nothing to do with the previous ones, which is a family of Desargues triangles. And this is now I can redo the exercise of seeing if the Desargues triangles are in perspective with the others. So I start a kind of bottomless research, which achieve, I think, the idea of complexity I've evoked at the very beginning. That's it.